This is a story from the year 1586 in England. Queen Mary of Scotland is standing trial for treason in an English court. She is accused of plotting the murder of the English Queen, Elizabeth. The only evidences produced in the court were letters written by Queen Mary. These letters were written by Queen Mary from her prison cell. It showed her participation in the plan of murdering the Queen of England, Elizabeth. The only issue with the evidence was that none of the letters were written in a readable format. Though it contained the English alphabets, the words made no meaning. It was like reading a gibberish letter. What Queen Mary produced was a cryptic letter. Its meaning can only be understood by her since she created the letter. If someone else would want to understand the hidden meaning of those words, they will have to know the key. The word cryptography comes from the Greek word, kryptos, which means hidden, and graphein, which means to write. The hidden meaning depicts the kind of letter created by Queen Mary since the context of the message is unknown to the reader. There is another form of secret communication called steganography. The word steganography again comes from the Greek language's word, steganos, which means covered. The actual message is covered in this form so that anyone else doesn't know the existence of the content. In olden days, a common method for secret communication was to shave the head of the messenger and then write the secret message on the scalp. After waiting for the hair to regrow on the scalp, the messenger can wander freely without the fear of getting caught. Let's take a look at one of the modern form of steganography. Text can be always covered with some image on top of it. The word cryptography comes from the Greek word, kryptos, which means hidden, and graphein, which means to write. The hidden meaning depicts the kind of letter created by Queen Mary since the context of the message is unknown to the reader. There is another form of secret communication called steganography. The word steganography again comes from the Greek language's word, steganos, which means covered. The actual message is covered in this form so that anyone else doesn't know the existence of the content. This is a story from the year 1586 in England. Queen Mary of Scotland is standing trial for treason in an English court. She is accused of plotting the murder of the English Queen, Elizabeth. The only evidences produced in the court were letters written by Queen Mary. These letters were written by Queen Mary from her prison cell. It showed her participation in the plan of murdering the Queen of England, Elizabeth. The only issue with the evidence was that none of the letters were written in a readable format. Though it contained the English alphabets, the words made no meaning. It was like reading a gibberish letter. What Queen Mary produced was a cryptic letter. Its meaning can only be understood by her since she created the letter. If someone else would want to understand the hidden meaning of those words, they will have to know the key. This is a story from the year 1586 in England. Queen Mary of Scotland is standing trial for treason in an English court. She is accused of plotting the murder of the English Queen, Elizabeth. The only evidences produced in the court were letters written by Queen Mary. These letters were written by Queen Mary from her prison cell. It showed her participation in the plan of murdering the Queen of England, Elizabeth. The only issue with the evidence was that none of the letters were written in, though it contained the English alphabets, the words made no meaning. It was like reading a gibberish letter. What Queen Mary produced was a cryptic letter. Its meaning can only be understood by her since she created it. If someone else would want to understand the hidden meaning of those words. The word cryptography comes from the Greek word, kryptos, which means hidden, and graphein, which means to write. The hidden meaning depicts the kind of letter created by Queen Mary since the context of the message is unknown to the reader. There is another form of secret communication called steganography. The word steganography again comes from the Greek language's word, steganos, which means covered. The actual message is covered in this form so that anyone else doesn't know the existence of the content. In olden days, a common method for secret communication was to shave the head of the messenger and then write the secret message on the scalp. After waiting for the hair to regrow on the scalp, the messenger can wander freely without the fear of getting caught. Let's take a look at one of the modern form of steganography. Text can be always covered with some image on top of it. An even better approach is used in microdot strategy, which was prevalent during Second World War. The actual message was photographically shrunk to a small dot, which can be later used in place of a tittle of alphabets like I, J, or even as a The main drawback with this form of communication is if the message is uncovered, the entire communication is jeopardized. This issue is tackled with cryptography, where even if the message is intruded by a third party, the meaning still stays hidden. Unless that message is decoded using the key. In a secret communication, there is a sender who initiates the message and creates the cryptic form of the message. This creation of a cryptic message is also known as encryption. The original message is encrypted using a key. This is nothing but the logic or steps performed to hide the meaning of the message. There are many different ways in which a key can be chosen, and we will see a variety of different ways in this course. The receive. This process is the opposite of encryption, called as decryption. It is important that the same key is used for encryption and decryption, else the actual message can be lost in translation. An important aspect of this practice is the people in charge of encrypting and decrypting messages. Codemakers are the people who find new keys to make their message unbreakable, whereas codebreakers are the people who try to guess the key to break the message. A codebreaker was able to decrypt the letters of Queen Mary. This exposed her allegiance to the murderers, and henceforth she was beheaded. Efficient communication always relies on the prowess of codemakers and codebreakers. In the coming topics, we will be seeing the different methods of encryption and decryption. It's time to now look at what have we learned so far with a small quiz. This completes our topic on a brief introduction on secret communication. That is all. From our last topic, we now know that cryptography has been used for a long time. This brings us to an important aspect of this form of study. Technology has played a vast role in transforming cryptography. In the olden days, the means of communication were quite limited. The most popular device was something which is still used by us, paper. With this, cryptography was always limited to a certain standard. The best bet for this was creating something gibberish at first look. Just like what we saw with Queen Mary's letters. It means the classic way of secret communication was substitution of letters. The sender has to rely on particular steps to convert the actual letter into a ciphertext. The most feasible method is to replace letters with other letters. So each alphabet can be replaced by one of the other 25 alphabets, if looking at English language. Even numbers can be replaced by other numbers. Or maybe by some other alphabet. But, do you think, our kings and queens had known only this method? One can create a ciphertext even by employing pictures or drawings. So each message. The interesting bit in this method is that it is the oldest form of cryptography. Of course, because language came in picture quite later. This method of employing pictures instead of words is known as hieroglyph technique. It was used by Egyptians close to 4,000 years ago. The message used to be secretive and understood only by the scribes who transmitted or received this. But this method was not used much going ahead because of widespread use of language as a means of communication. Classic. The message's secrecy lies in the method which the sender has used. This secret method should be known to the receiver to decrypt the message. More importantly, the entire process of message passing should also happen secretly. Since we are just using substitution of letters only, an intruder is capable of decrypting the message. We all saw Queen Mary's fate even after using cryptography. Cryptography has been improved a lot because of technology. We already know about the microdot method used in World War II. Such methods were possible because of the progress made in technological landscapes. The biggest advantage in modern methods is the use of binary codes instead of alphabets. With computers, the paper letters were replaced by digital format. A single letter like C on paper is quite different when seen on a computer screen digitally. It is known by binary codes and therefore C becomes 01000001. These codes increase the possible combinations in which a message can be encrypted. These large number of combinations broaden the usage of mathematics to create algorithms for encryption. Now, let's look at some features of modern cryptography. Modern methods of cryptography use bits instead of letters. The methods used for encryption are complex mathematical algorithms. But the interesting bit is these algorithms are publicly known. Each sender and receiver has their own private key with which they encrypt or decrypt the message. This makes the message passing free of secrecy, so that intruders cannot merely guess the message. Even if they can, it will take them a lot of time, which defeats the purpose of stealing. The modern methods. Therefore, in this course we will be looking at both the methods. But it is easier to understand the classic ones, and therefore this course will cover the traditional ones more. In the coming topics, we will be seeing the various ways in which ciphertext is created. It's time to now look at what have we learned so far with a small quiz. This completes our topic on some distinguishing factors between classic and modern methods of cryptography. That is all. We all have heard or read about the Roman dictator, Julius Caesar. He was one of the finest military generals of his time. Probably thousands of years ago. He was a staunch believer of secret communication while passing messages to the leaders of his military campaign. He knew the consequences of information leak and therefore devised his own way of tackling it. A simple shift cipher was probably his brainchild. In this cipher, we shift the plaintext for this predefined number becomes our key. The alphabets are supposed to be placed in a cyclical manner such that a shift from the last alphabet, Z, shall result in the first alphabet, A. We have already seen a simple example of Caesar cipher in our previous topic. The letters from Queen Mary. By now, you must have already guessed that Caesar cipher and shift cipher are interchangeable. However, a Caesar cipher is the one where a plaintext coding is blessing. Can be encrypted using a Caesar cipher as ciphertext, FRGLQJLVEO. Though, we can use any key for the encryption. The decryption process is exactly the reverse of encryption. Instead of adding the key position, we need to subtract the key position to get our plaintext. Shift ciphers are pretty straightforward and therefore the security provided is also of a very basic nature. One of the biggest disadvantages of Caesar cipher is the limited number of key available. With each language coming with a finite set of alphabets, the key also becomes finite because of this reason. So with English language, there are only 26 keys possible. This way, a codebreaker can give all his time to try out each possible key and get the exact plain text. Even with the drawbacks of Caesar cipher, it continued to rule the cryptography charts for many years. In order to build a more secure form of communication, codemakers created another cipher known as substitution cipher. As the name suggests, instead of shifting alphabets to create the ciphertext, this form of cipher substituted the alphabets. Substitution cipher is also pretty easy to implement. In this form of cipher, each alphabet in the plaintext can be substituted with any other alphabet. So in our example above, A will be substituted with T and B will be substituted with X and so on. This change from the shift cipher increases the number of combination for a key astronomically. From a mere 26 combinations, this substitution cipher has approximately 10 to the power of 26 combinations. This is possible because each alphabet in the plaintext can take up any one of the 26 alphabets. As the message gets longer, so does the number of combinations. But there is one major drawback with this form of cipher. The key becomes a major part of the secret communication as the entire encryption is dependent on knowing the substitution letter for each alphabet. With shift cipher, the key was just a number which can be easily memorized. The same is not possible with substitution cipher. To overcome this obstacle, codemakers came up with a different approach of randomizing the ciphertext. The idea was to choose a smaller word which can be easily memorized. Say, programming is chosen as that word. Now, we need to remove the duplicate alphabets from this keyword and write it again as. Post this, the remaining alphabets of the language are added to this cipher in their known order as. As you might have observed, with a simpler key approach, many of the alphabets are chosen same after their substitution. In our case, the latter part of the plaintext and ciphertext remains unchanged. Therefore, it is recommended to use a sentence as a keyword rather than a single word. In this topic, we saw two of the most basic traditional ciphers used in some of their features. In the next topic, we will be seeing the various ways in which ciphertext is analyzed and broken. It's time to now look at what have we learned so far with a small quiz. This completes our topic on traditional ciphers. That is all. We have already seen few cipher codes in the last topic. The codemakers have done a phenomenal job. In order to break it, the probable key should be used multiple times until a hit occurs. Codemakers were doing a phenomenal job, but researchers had already started studying methods of breaking the cipher. The study of destroying a cipher is known as cryptanalysis. In this study, the codebreaker has no clue about the key but still manages to decipher the message. As we know that cryptography has been in use for thousands of years, the art of breaking the cipher also goes hand in hand. While the cryptographers were busy in developing new ways of secret communication, the cryptanalysts were looking for weaknesses in the same. The first mention of cryptanalysis being successfully employed appears in Arab literature. We know that cryptography is related to literature since it deals with alphabets and text. The earliest form of literature analysis was done by Arab theologians. Their task was to collate all the revelations received by Prophet Muhammad but in a chronological manner. In order to do this, they employed a simple yet effective method. The method was to calculate the frequency of words in each religious text maintained and keep an eye for newer words being encountered. If a new word was encountered, it meant that the word has been recently evolved. Therefore, this text comes later than other texts where the word has not been mentioned. The scrutiny didn't stop only at words. The next logical step was to look at the frequency of alphabets used. This was nothing but inventing the most common technique of cryptanalysis, frequency analysis. Arab philosopher, Al-Kindi, is often regarded as the first person to produce papers on this form of breaking codes. First step is to be sure if you know the language in which the ciphertext is available. From the same language, take a plain text which is fairly longer than the ciphertext. Count the occurrences of each letter and rank them from highest to lowest. Perform the previous step on ciphertext and rank its occurrences as well. The idea is that the most occurring letter in ciphertext can be replaced with the most occurring. Similarly, the second most occurring letters from the plain text can be swapped with the respective letter from ciphertext. Frequency analysis doesn't guarantee a correct output always. But it can surely point in the correct direction. This technique does require a fair bit of understanding of the language, intuition, and some guesswork as well. It will be clearer once we take an example. In order to put our code-breaking prowess at test, we decided to try this technique ourselves. At Programming Hub, we created 3 teams. Team A would provide the ciphertext to be decoded. For this, they can choose any text in English from internet. They encrypted the message with substitution cipher as discussed in previous topic. Team, they obviously just rummaged through internet to find this. Team C is our code-breaking group. The image shows the ciphertext provided as an input by Team A. It is completely gibberish and but still, they destroyed it within a matter of minutes by using frequency analysis. For notation purpose, we will be keeping ciphertext in lowercase letters, whereas the plain text will be shown in uppercase letters. This helps in visualizing our efforts. Team C followed the steps of frequency analysis and counted the occurrence of each letter in the ciphertext. At first, it looked like a daunting task, but few Excel-based formulas got us rolling in no time. Following table gives the frequency analysis of ciphertext. Now, with these two tables we can map the high-occurring letters in plain English with the high-occurring letters in the cipher. In English as a language, letters E, T, A and O are the four most used letters. First attempt will be to substitute R, B, N, G, equals, E, T, A, O. Our first target will be small words, one-letter, two-letter and three-letter word. The only possibilities for one-letter words in English are A and I. Similarly, the most common three-letter words in English are the and. Some of the notable two-letter words are in, on, us, of, we, so to in, etc. This shows our substitution for R, B, N, G, equals. We still don't know if R, greater than N or T or A or O and likewise. Looking at this image, things doesn't seem to be correct. Team C saw that a two-letter word has been decoded as ought, which clearly is, so the combination was changed to R, B, N. This changed the two-letter word to two. Damn right. Also, we saw two occurrences of two at. Any guesses? U, greater than H, which makes the word that. These observations made us believe that the mapping of E, O, A, T is correct. We had another two-letter word as AF. Looking at our two-letter word list, it could have been as, at, or AM. Since T is already mapped, we went ahead with the probability of F, greater than S. The team also found a three-letter word as OC. So, A, greater than N and Q, greater than D were deduced. Till now, our list is R, B, N, G, U, F, A, Q, equals, E, O, A. With 8 letters done, the team started guessing letters. Yast yond equals last long. Suni equals sooner. Offensive equals offensive. The last one was obviously a huge guess, but it highlighted one important point. After tackling small words, it is time to hit the consecutive appearances of cipher letters. So SS and offensive gave way to FF. With all these substitutions, the cipher looked as shown above. The team could see some 4 and 5-letter words already deciphered. With just 4 rounds of substitution, it gave way to newer words. This cipher is about to be crushed. Our 4th attempt gave way to words like this. Intellectual equals intellectual. Zodern equals modern vertical bar. Azarapan equals American. Newton equals Newton vertical bar. J Olden equals wouldn't. Traffic equals traffic vertical bar. Recorded equals reported. Let's put these in as well. The cipher is almost broken now with just few letters remaining. By this time, Team C made a quick and neat observation. This pattern was occurring in all the letters, and it turned out to be the sad demise of Team A, who created the cipher. The final broken message looked something like this. It became clear that Team A used rotation cipher, which provides the cyclical nature of substitution. If this is detected by the cryptanalyst, the greatest ciphers are broken very easily. We will learn more about the cyclicity in the coming topics. So now we have seen a working example of frequency analysis. It points in the correct direction and the whole process speeds up with every pass. In this example, there were spaces which made us identify small words. But it won't be the case always. In such situations, the concept of vowels and consonants. Nevertheless, even without spaces, a substitution cipher is vulnerable. Obviously, the codemakers now had a task in hand. In this topic, we saw a working model of frequency analysis. In the next topic, we will be seeing how codemakers made newer improvements to defeat this analysis. It's time to now look at what have we learned so far with a small quiz. This completes our topic. That is all. In our previous topic we learned about cryptanalysis. We now know how vulnerable ciphers can be. An important point to discuss over here will be the types of ciphers. You may be asking what was so common between them? Well, the answer lies in the repeatability of cipher produced. Same plaintext alphabet will result in same ciphertext. This is the reason why frequency analysis disrupts the whole system. Remember the guesswork and substitutions we made in our previous topics. Once we deduced that R in ciphertext is E of plaintext, it stood true for the entire. Each R in the ciphertext was replaced with E. This property is what makes a cipher called as monoalphabetic substitution. Polyalphabetic substitution was the idea was simple: same plaintext alphabet should result in different ciphertext. This way the codebreaker's job will become daunting as each alphabet will be pointing to a different plaintext. The final development of polyalphabetic substitution was done by a French diplomat, Blaise de Vigenère. Let's have a look at this cipher's method of working. It is nothing but the usage of multiple monoalphabetic substitutions in a single cipher. To begin with, this can be any word or sentence. If this key phrase is known or leaked, then the task of deciphering becomes easy. Our plaintext is as shown in the image above. It's a random quote and not anyone's personal opinion here at FUB. Our chosen key phrase is snoozer. Our first step will be to convert each alphabet in the key phrase into its numeric order. So S, N, O, O, Z, E. E is converted to 5 because it is the fifth alphabet in English, and so are others changed to their respective number. Since our key is 7-letter long, after each seventh letter of plaintext the key is repeated again. This image gives us the enciphering of first 21 letters from our plaintext. Instead of shifting each alphabet by same key as performed in Caesar shift, here each alphabet is shifted as per its designated key value. Also note that same letters in plaintext generate different cipher alphabet. This is the reason behind its polyalphabetic nature. Vigenère cipher enjoyed zero competition from codebreakers for close to 2 centuries. The obvious drawback with the system was its complexity to implement. This cipher was used prominently in 17th and 18th century. Obviously, everything was on paper and therefore shifting each letter different number of times was an arduous task. The codemakers kept a ready form of this cipher, also known as Vigenère square, to supplement their encryption activities. The Vigenère cipher was eventually broken in the 19th century by Charles Babbage. The most important point, as in our example, we know that snoozer is 7-letter long. This means that each first, 8th, 15th, 22nd letter of the plain text are enciphered by the same key phrase letter, Z. Thus all these, we have already seen the usage of frequency analysis on such ciphers. Similarly, each 2nd, 9th, 16th, 23rd letter of the plain text are enciphered by the key phrase letter, N. This way the entire cipher can be broken down into different parts on which analysis is performed. But the main trick lies in identifying the length of the key phrase. This in turn depends upon looking for repeated patterns in ciphertext. The distance between this recurrence tells about the probable key phrase length. Therefore, a Vigenère cipher can be made unbreakable by using a key phrase which is as long as the plain text itself and is this way there won't be a recurrence which can give away the length of key phrase. This cipher is known as one-time pad. The usage of one-time pad is fairly limited, because it is quite time-consuming to create long key phrases at random. In a military setup, till now we've seen ciphers where the plain text is changed to some other letter. The source input is changed to create an absolutely new input. Let's look at a cipher which doesn't work on substitution rule. In transposition cipher, the plain text is merely rearranged to give it a cryptic and gibberish look. One such cipher is known as simple columnar transposition. In this method, the plain text is placed in table format. The columns of this table are then rearranged to create the ciphertext. In this cipher, let's say our plain text is, lack of government funding hampered back. We decided a key of 10 columns. The method of obtaining transposition cipher is to, this way we will get an image as shown above. The ciphertext is formed by writing the code vertically instead of horizontally. Ciphertext, Lrido an Berkmgakaho Navmagfguaven residue. The receiver will be already knowing the key, which is the number of columns. He or she will place the ciphertext as shown in previous image to reveal its content. Thus, not a single alphabet is substituted but still a ciphertext is created. In this topic, we saw polyalphabetic substitution cipher and transposition cipher. The idea was to know more about how the battle between codebreaker. It's time to now look at what have we learned so far with a small quiz. This completes our topic on traditional ciphers. That is all. We have seen a brief history of how ciphers were created and even how all of these developments kept happening on a paper. In military communications itself, there will be thousands of messages that needs to be passed. The process of encryption was coming at a huge cost in terms of time taken. Ever since Charles Babbage decoded the Vigenère cipher, the codemakers kept on hustling for a new cipher. To add to their misery, early 20th century paved way for radio communication. With this advent, the need for telegraphic lines, wires, was eliminated. Mankind was moving towards faster ways of long-distance communication. The news of radio communication was received by military units with rejoice and worry at this. The good part was the speed with which communication with men on the field can be established. The bad part was that the process of encryption wasn't fast enough to go hand in hand. To add to their woes, radio communication was not very secure. In fact, an enemy can receive the same signals being transmitted from a particular base. The entire onus felt on how secure an encryption process be so that the decryption cannot be done by enemies. During the build-up to Second World War, Germany had their sight on making the encryption as fast as possible. The need was for faster and more secure ciphers. They found an answer to this in a bunch of motors moving around in tandem. Enigma machines were electromechanical rotor machines that eased the process of encryption. It was invented by German engineer Arthur Scherbius. This machine was created to protect commercial communication but was largely utilized in military operations. At first look, one can easily misunderstand an Enigma machine for a type. To begin with, it does have a keyboard to input a message. But more like levers of keys. The output is a series of lamps designating one alphabet, placed on a lamp. For each pressed key, the encrypted alphabet glows up. This way there is no need of paper trail to do any calculation. This setup is a very basic, so for performing encryption, each letter is pressed and the corresponding lamp which glows is noted down. But just like any modern-day machine, before one can start using it, and so, even Enigma needed the same. Going into the detailed architecture of an Enigma machine is out of scope of this topic. But still we would like to give a brief overview of the machine for the sake of completeness. And so we present to you, Scrambler, the most important component of encryption in Enigma.